Okay, so I'm going to bring up the simulation on waves again, because today we're going to continue talking about waves, but we're going to do something a little different from last time, which is we're not going to be talking about waves particularly in the string, but more general waves. But I'm still going to use waves in a string to sort of, I guess, demonstrate something. So let me get that available for you. This will be, I think, a fairly short lecture today, which I'm sure is, terribly disappointing. Okay, so hopefully most of you were able to do this, and what I wanted to talk about was what happens when we have a loose end. So if I want to get a standing wave with a loose end, so I'm going to turn the amplitude down. And, if I change the frequency a little bit, just going to try to find a standing wave pattern here. Let's go down in this ballpark. Okay, so that's pretty close to a standing wave pattern. If I can get really right on the right frequency, we should see the amplitude going up. Should see that. Let me turn it up a little bit, because I don't actually have to find it exactly for this purpose. So if I pause this, then what we can see, let me just step it a little bit more. Okay, what we see is one antinode, and then another antinode, and then a third antinode. So we have one complete wave, and then a quarter of a wave. And what happens with the open end is that if we look at the end always becomes an antinode. It never becomes a fixed point because it can slide up and down. And so as we go, in this particular case, if I wanted to figure out how the wavelength of the wave relates to the length of the string, we have kind of, if we would think of splitting this string up into 5 quarters. So the first quarter is here, the second quarter is here, the third quarter is right there, the fourth quarter, and the fifth quarter. So technically, or I guess these are fifths, sorry, not quarters, but the first fifth, second fifth, third fifth, fourth fifth, and the fifth fifth. So the length of the string, or the wavelength, would be exactly 4/5 of the length of the whole string. So let me put my whiteboard up so I can kind of draw some pictures. So if I have a string that has, a loose end and more or less a fixed end. So instead of, taking the end and going up and down, we could just kind of turn off the oscillation or just vibrate it with a bow or something, and we would just see these standing waves. If we have no friction, they just kind of keep going. And what we can have is our very first frequency would be one where it just goes up and down, and there's no nodes in between. So we have a node, and then an antinode. the very next one, and in this case, the length here it's really getting just 1/4 of a wavelength. Because remember, from one node to the next node is half of the wavelength. So we're going from one node to an antinode. That's 1/4 of the wavelength. That's 1/4 of the wavelength. If we do it again, but this time we want to have still an antinode on the right and a node on the left. Anti. Okay, so but we want to have one more node, then that node would have to be something like here, or it could do, wait a second, I want to do just one node. So it would look something like that. And in this case, you know, this distance would be lambda over 2, and that would have to be 2/3 of the length, because there's going to be equal distance between the end point, the antinode, the node, and the next antinode. Always equal distances between those guys. So if we rearrange this, we could say that lambda is 4/3 L, where here lambda is just 4L. And we can keep kind of going to see how this is going to work. So if I want to put 2 nodes, it's probably not quite spaced properly, something like that. So we have a node, another node, antinode, antinode, antinode. And so in this case, as I discussed before, wavelength, there's 1, 2, 3, 4, 5 sections, and the wavelength is 4 of those sections, so that's 4/5 of the length. And so let's see if we can find a pattern. We've got lambda equals 4L, lambda equals 4/3 L, lambda equals 4/5 L. So lambda seems to be equal to 4L over something. And, you know, for the first harmonic, we should just get a 1 down here. So maybe we think, aha, maybe what we have is just N. But if we tried that out for 2, that's not right, because it should be 4/3. So then we could try something else. Maybe it's 4L over 1 plus 2 times N. Or maybe let's try 2N minus 1. So if that's lambda N, then lambda 1 would be 4L over 2 times 1 minus 1, which is 4L over 1. That's correct. Lambda 2 would be 4L over 2 times 2 minus 1. Well, that's 4/3 L. And lambda 3 would be 4L over 3, or 2 times 3 minus 1, which would be 4/5 L. And so a pattern like this looks like it will work. Any questions so far? Okay. So if we have a situation where both ends are open, That is, both ends are loose. Then what kind of waves could we have? Well, we could have them both just going up and down at the same time. We could have it so that one end is up there while the other end is down there. So let's see if I can't really do that on the simulation, but what would happen is it might start out looking like this middle line. This would be kind of step 1, and then maybe as a step 2, it goes to there, and then step 3, and then step 4, step 5, step 6, step 7. So just to show you the progression, it starts off like this line, and then it moves like this, and then it gets sort of to its maximum value, and then it starts to get smaller again. It goes back to the middle, and then it goes up, and the opposite side becomes a peak, while we start off, the left side becomes a peak while the right side is a trough, and then the left side becomes a trough while the right side is a peak, always in opposite fashions. Now, it's kind of hard to imagine exactly how we could do this with a string, but it could be not that it's not a string. It could be that it is a pipe, and we're blowing air through the pipe, and the air makes the pipe vibrate. So this is basically how a flute works. And if both ends of that pipe are open, then we will get a certain series of standing waves where always we have antinodes at the end. Or we could have a piece of wood that is maybe mounted on something, and then we hit it with some kind of a little mallet. And when we do, it's going to vibrate. And when it vibrates, we will have a fixed point in the middle, but the ends are going to go up and down. Okay, so basically, depending on the geometry, that's going to help us draw pictures and find patterns of standing waves. Any questions so far? Okay, so I wanted to look at a couple of problems in the book that relate to this idea. Let's open up college physics and okay, so we're going to do problem 22.15. And it says we have a rod 200 centimeters long, clamped 50 centimeters from one end. So we have a rod, and its length is 200 centimeters. And then at the 50 centimeter mark, so I'm kind of thinking this is 50 centimeters, 100 centimeters, 150, and 200. 0 on the left. So it's clamped. It is set into longitudinal vibration by an electrical driving mechanism at one end. The frequency of the driver is slowly increased from a very low value, and the rod is first found to resonate at 3 Hz. So what does that mean? The resonance is when we hit that right frequency that creates a standing wave pattern. And so the first standing wave pattern we get, we could call the F1, is 3,000 Hertz. So, and let's see, what is the speed of waves in the rod? Okay, so we want to know what's the speed. So the first thing we have to do is figure out what is it going to look like, what are the waves going to look like, because that's going to determine our wavelength. So the logic is as follows. It's clamped at the 50 centimeter mark. So we must have a node there. Okay, there must be a node there because it's clamped. And the ends are free. So it must have antinodes at both ends. So if I have an antinode at the end and a node here, there's a lot of different patterns. It could kind of do something like that. That would be a very small wavelength and a high frequency. I want the lowest frequency possible because they told me this is the starting at low frequency and increasing. This is the first time I got a standing wave. So it's not going to look like this blue one. It's not going to have lots of waves, and therefore remember small wavelength means high frequency. I want the longest wavelength I can get, and that's going to come when we have an antinode at end and no nodes in between that antinode and this first node. So it's going to look like this. And then just to keep, if it's 50 centimeters from antinode to node, it must be 50 centimeters from that node to the next antinode, and then 50 more centimeters to the next node, and then 50 more centimeters to the next antinode. So this is what the wave must look like for the first standing wave that we find. This is the simplest one with the least amount of nodes, and we can see there's 2 nodes there. Okay, but this would be the fundamental frequency. So what's the wavelength of this thing? The wavelength is the distance from one peak to the next peak, or twice the distance between the nodes. So the wavelength, the lambda, is just 200 centimeters. So we want to know the velocity. That's going to be frequency times wavelength. That's 3,000, per seconds times 2 meters. I'm just going to write that in meters. And that's 6,000 meters per second. Okay. Questions about this problem? Haley.
Okay, so I'm understanding how, since it's clamped, we know that there's a node there.
Mm-hmm.
You say that there's a second one at the 150.
Yes.
How do we know that?
We only know that because we kind of worked our way from the end point. We know there's an antinode on the ends. And so if there's an antinode at 0 and a node at 50, the next antinode, they're going to be spaced in 50 centimeter increments. So antinode, node, antinode, node, antinode. That's it. Just they have to be spaced 50 centimeters apart.
Okay.
All right. Other questions? I can't. I heard a hand, but I don't know. Is it just Haley raising her hand over and over again? No? Ziad, do you have a hand up?
Yeah, I just wanted to know how you knew the wavelength was 200 centimeters.
So the rod is 200 centimeters. So you want to know, how do I know the wavelength is the entire rod?
Yeah.
Yeah. Basically, you get wavelengths. So suppose I have a wave, and it's got lots of stuff for me to look at. I can pick any section of this wave where I go from a maximum to a maximum, or a minimum. Let's pick a different color. A minimum to a minimum, or it's a little bit riskier to pick a node because the next node is not a wavelength. You have to skip a node. So you can go from a peak to a peak, or a trough to trough, or valley to valley, or you can go from a node skip a node, and the next node over. Doesn't matter. Those are three different ways of seeing it. In this particular case, I don't have enough nodes to, like, there's a node here, and there's a node here, and the next node would be over here. So if I wanted to do that, that's fine. I can imagine from this node, 2 nodes over, that would be a wavelength as well. But what I did is I picked the peak to the next peak. So basically, we're looking for a pattern that repeats itself. And that pattern that repeats itself, if I'm going from node to the second node to the third node, it looks like that. But if I want to go from the bottom, the trough to the trough, that pattern looks like this. And if I want to go from you know, peak to peak, then it's from here to here. That's what I did. I went from here to here, and that's 200 centimeters. Does that make sense?
Yeah.
All right. Other questions? Okay. So again, the idea is we really have to draw a picture, and we have to use a logic and think about, you know, wherever the thing is clamped has to be a node, and the end has to be an antinode. And, you know, if this thing were spaced 210 centimeters long, if it were 210 centimeters long, then this would not be able to create a standing wave. It's required that I have an antinode on both ends and a node where it's fixed. And so if this were longer, I might have to go through all kinds of, it may have to do some weird thing in order to have an antinode on each end and to be fixed in the middle. And that's something that, I mean, we won't see any that are really hard like that where the numbers don't come out nice, but in principle, it could be anything, and that's how, you know, a xylophone or something along those lines works. The frequencies, by changing the length of the rod and where it's clamped, that's what kind of determines the note that that's tuned at. Okay, so let's try another problem. The next one says, determine the shortest length of pipe closed at one end that will resonate in air when driven by a sound source of frequency 160 hertz. Okay, so we have a frequency which is 160 hertz. And this, we can think of this as the fundamental frequency. And the speed of sound in air is 340 meters per second. And we want to know the length of this pipe if it's open on one end. So it's closed on one end and open on one end. Okay, so first of all, we want to know what is the pattern that we're going to see here. And so it says the shortest length of pipe, so that's kind of the extreme. We're looking for the lowest frequency that we're going to see. So when we have a pipe that's open on one end and closed on the other end, what that means is that we must have a node on one end and an antinode on the other end. So open means antinode, closed means node. Or it's like fixed versus loose. So the different frequencies we could see here, we could have one that, hold on, let me change colors, just kind of goes up like that and goes down, and what we're getting there looks like 1/4 of the wavelength. Or we could have one where we have kind of half a wavelength and an extra quarter. Okay, so hopefully you can see the difference between the red and the green one. If not, if you have trouble telling the difference, then just, one pattern looks like this, and the other pattern just looks like that. Okay, so in these two cases, this one would have the wavelength. Well, how do we determine that? This is 1/4 of the wavelength. So 1/4 of the wavelength is the length of my pipe. And so lambda would be 4 times L. In this case, what we're getting here is kind of a half a wavelength plus a quarter. So follow one of these, it's like a half, and then it gets from a node to an antinode to a node to an antinode, and we're missing kind of the last bit that would take us back to a node. So we have 3/4 of the wavelength is equal to the length, or that would say lambda equals 4L over 3. Now, we have a frequency and a velocity here. We know the frequency is equal to F times lambda. And so the lambda is just V over F, which is 340 over 160. Let's see what that is. That's 2.125. And that's going to be meters. And what we want to do is we want to find the shortest length possible. So if we look at these two guys and we solve for length, well, okay, so length, we have solved for length there and there. So the shortest length is going to come from this one, where we have the length is 1/4 of lambda. The next harmonic has length equals 3/4 of lambda, and you might guess the next harmonic that we didn't draw would be 5/4, and then 7/4, and so on. So it wants the smallest length. That's going to be from this fundamental frequency. And so the length is 1/4 of the wavelength, which is 1/4 times 2.125 meters. And that's about 0.53 meters. So if you want to make yourself a set of pan pipes, or maybe take PC and make pipes that you can just kind of hit with things and play notes, this is how you would determine the length of the tubes. Of course, the speed of sound and air is different. So if you're blowing across the pipes, the speed of the wave is this. If you're hitting the pipe, then it's going to have to do with stuff like the material the pipe's made of, how rigid it is, and things like that. Okay, any questions about this problem? All right, so you have maybe 2 or 3 problems like this for homework for tonight, and then you're done. So let me just comment a little bit about what you should be doing from now going forward. If you haven't done the lab for today, you should finish that up. If you're having trouble with it, let me know, and I'll try to help you. I have gone through all of the corrections people submitted before Monday, And so I'll continue going through those today, and most of the ones people submitted since then. And I'll try to get these the waves in strings lab graded ASAP so that you can still make corrections. But you should, if you have corrections to make, you should definitely get those done as soon as possible, because once I regrade it, if there are still problems, you can still submit corrections. But I really can't take them after Sunday because that's the last day of the semester. And you don't want to be turning in a whole bunch of corrections then and then lose a bunch of points because there's no, you forgot to write units on your corrections or something. And it's a really simple problem, but there's no time for you to resubmit. So if you can get corrections in sooner, that's better to help you make sure you get the full points. Please remember that I only take the 10 best labs. So if you already have like 10 good labs you're happy with, you don't have to make corrections on that 11th lab that you have trouble with, although you're welcome to do that. So I take the 10 best grades on labs. You should be studying from now until Sunday, partially for this next contest, partially for the final. I would probably be doing that about 50-50 by this point. There's not a lot of material on this upcoming contest, so particularly if you're caught up to date on homework. We don't have lecture tomorrow, so that's, there's no more work after today's homework. So you should, try to get that homework knocked out and then start reviewing for this contest, but really more for the final. For this contest, the homework should be kind of getting you prepared pretty well. But for the old, for the old material, you really need to sit down and start working some problems again to refresh your memory. And then, we will not have class tomorrow, but I'm available if you have questions, so just let me know. And then contest on Friday, contest on Sunday. This may be the last time that I interact with you if you don't have questions, so I appreciate those of you who've been coming to class. I really appreciate your attention and questions and everything, and good luck next year wherever you wind up. Thanks a lot. Anyone have questions for me before we go? Elise?
The final exam on Sunday is at 2 p.m., right?
Yes, I think that's correct.
Okay.
I should ask, while you guys are still here, did you guys like having the equation sheet as a separate tab better than having it at the top of the contest, or the same or worse? Anyone have input on that? Haley?
I liked it more, so I didn't have to keep scrolling up and down. I liked it better.
Okay. Anybody who did not like it? Okay, so I'll just keep that format for the 2 upcoming contests, especially on the final. It's going to be several pages of equations. I'll try to get the equation sheet up for Friday and for the final soon, so you can take a look at them. I guess last thing, if you've made corrections, or there's some grades missing, something that you sent me an email. It's really hard for me to keep track if you sent me an email instead of posting to Blackboard. Go ahead and send me another email to remind me, because I get a lot of emails from students, so it's really easy for me to, if I don't address one right away, that's like kind of like I submitted here, or remember I sent you this email 2 weeks ago. Just remind me what it is that I still haven't graded or addressed if you and I have had already a conversation about something, because I want to make sure that I get everything covered. That's it. Thanks a lot. As always, if you have questions, stick around. Otherwise, I may or may not see you again. Thanks a lot.